Well, welcome back, everybody. Thanks for bearing with us as we navigate some of these technical details. Hope you had a good time in the breakout session. We had a really fantastic group, lots of interesting resource management problems. We ended up focusing on snakes on Guam, which was really cool. Very complicated, lots of very interesting management issues there. So in this last session of the day, we're going to be focused on starting to bring together adaptive management with a bit more of a structured formal presentation of Markov decision problems, which are these adaptive management problems are definitely part of that class. We know that a lot of significant environmental problems involve taking action over time under uncertainty, but also with the potential to learn as the future unfolds. A lot of us might be interested in natural resource problems like fisheries management and invasive species. That was certainly a key focus of our breakout group. We also talked about water pollution. There's some important learning problems in greenhouse gas policy that we're facing. So this is really pervasive across a lot of different environmental areas. There are some common features of these adaptive management problems that show up on a repeated basis. That is that we've got repeated actions over time. So we're not just taking a choice today or choosing an action today, but then again next month or next year, and then again a year after that, and so on. And we're dealing with rewards, but also opportunities for information that we can use to make better decisions in the future. So it's in this context where a lot of these interesting adaptive management problems lie. I want to take just a moment here to get a little bit more specific about what kind of adaptive management problem we might be dealing with in a certain context. So here's a breakdown of a taxonomy of different adaptive management types. I think what you'll see as you go across the literature, the way in which resource economists like myself or Paul Fackler or David Kling might, what we might be thinking of when we say adaptive management might be a little bit different sometimes than, say, somebody that comes from a computer science background or a conservation background. So I think it's important to get our terminology square. So a first key question is, is in the real world, is the manager going to update their beliefs, their understanding of the world as information arrives? And if the answer to that is no, then this is not adaptive management. If we have no updating of beliefs, no updating of our sense of the way the world works or what rewards look like, then we're really not in an adaptive management context. Okay, so we're much more concerned with this sort of context here where we're going to be learning over time. From there, a key distinction is the manager going to anticipate learning over time and take that into account when they make decisions? And then a second key dimension is whether the manager is going to intentionally influence the rate of information arrival. That is, intentionally probe, intentionally sort of change what they might do as an adaptive manager in order to influence either the speed with which they learn or the quality or the type of information that they get. So if we're in a case where the manager is forward-looking, they know that they're going to be updating their beliefs, and they're interested in probing the system to essentially use their management as to help drive experiments, we're in a context of active adaptive management. So I've got the acronyms spelled out up here, up in the top right. If instead, the manager is going to think of information as arriving exogenously, that is, information is going to arrive and I'm not going to pay attention to my capacity to speed up that information or affect that information, and I'm not going to incorporate it in deciding what I do today. I know that that information is going to come, but I'm going to treat it as exogenously arriving information. Then that's a passive adaptive management context. Now, there's one interesting sort of intermediate case here in between these two, where you treat the information, the arrival of information as exogenous, that is not something that the decision maker is going to influence. But at the same time, the decision maker is looking forward in time and saying, okay, I know that this information is going to arrive, and so I want to incorporate it into my decision making today. And I'll dive deeper into an example of this in just a moment. So we'll do basically a pencil and paper version of this sort of non-probing active adaptive management. This was sort of an interesting case. When we started to put together the materials for this workshop, it was clear to us what these two categories were, the active adaptive management and the passive adaptive management. But we weren't quite sure what to call this, what we ended up calling non-probing active adaptive management. And so it just sort of shows that there's various flavors of how these problems can be formulated that don't necessarily fit neatly into our typical conceptions of active or passive adaptive management. Okay, so we've just got some formal definitions laid out here just for reference, and we'll make sure and share these slides so that you'll have this available to you. But we're going to use adaptive management to apply to a dynamic decision-making context. So we're making decisions over time. And we are choosing optimally either in response to exogenous arrival of information that the decision maker is not driving the arrival of that information, or in an active adaptive management case, a context in which the manager is not just responding to new information, but also influencing the generation of this information by, say, probing the system. Maybe I allow my population to go a little bit lower than I otherwise would to see what it does there, or I allow my population to go a little higher than I otherwise would to see how it reacts at a high population level, using those management actions as experiments in some sense. And just a quick note here, when we say adaptive in adaptive management, we specifically mean adapting to new information. So Dave earlier on described what he called, I think, either a closed loop or a feedback rule. So a closed loop problem. That's where maybe you have some stock, maybe it's a stock of fish or a stock of trees or something, and you have some action that you're interested in taking, and the action that you take is not going to be constant as your stock changes. Maybe as the stock is low, maybe you take a little bit of harvest, or if the stock is high, you take more harvest. But you have this feedback rule where the state influences your decision. So that's not what we mean when we say adaptive. That of course it meets the dictionary definition of adaptive, but that's just a typical feedback rule or a closed loop kind of problem that economists and others have studied for a long time. When we use the word adaptive in adaptive management, specifically what we're intending to trigger is this notion that we're responding to new information that comes over time. We're responding to an updated understanding of either the physical states, if those are uncertain, or we're responding to new information about what a particular parameter level is or a particular functional form is that might be governing the population dynamics. So we're adaptive with respect to the arrival of new information, new knowledge. Okay, so this is our one-stop shop here for laying out what is formally a Markov decision process. And adaptive management problems are a particular kind of MDP, or Markov decision problem. The essential elements of an MDP are given by this set here, a set of 5 different objects. And Dave did a nice job of teeing up an intuitive sense of what these are. And we'll work over the next 45 minutes or so to lay out each of these in a bit more technical detail. So we've got state variables, action variables, some sort of transition probability, a reward function, and a discount factor. Now, a key bit of notation here to just bring your attention to is it can get a little cumbersome to time subscripts around all the time. So instead of always using, say, t plus 1, t minus 1, often we'll use just a plus sign to indicate one period into the future. So for example, instead of writing st and st plus 1, we'll just write s to indicate the current time period and s plus to indicate one period in the future. So for example, over here under the transition probability, what we're concerned with is, given the current state and an action chosen, what is the future state, S plus, the state in the next period? Okay, so that's a notation that we'll try to use when we're trying to keep things relatively concise and reduce the number of subscripts. Ultimately, with a Markov decision problem, our objective is laid out here at the bottom. That is to maximize or potentially minimize, but here maximize some stream of rewards over time that are discounted according to this discount factor that we'll talk a little bit more about later on. And what we've got here is summation notation that just means this is a sum from any given starting point of time t up through infinity. And of course, we could think about other time horizons as well. But we're going to spend a fair amount of time over the next, the rest of this session and then the additional sessions tomorrow, thinking more carefully about this object and how we solve it. And let me pause here because it sounds like there's a question from the chat room.
There's a question from, yes, basically this is a question about how non-probing AAM differs from PAM. They didn't understand the PAM.
Ah, sure. Okay. So let me clean up the slide here.
Yeah, I've just typed an answer to that question, by the way.
Oh, okay. Well, just
yeah, we don't see it, so I'm not sure you typed it in. We don't see it.
Oh, do I have to hit send?
I didn't.
Okay, I just sent it.
Well,
but that dismissed it.
Which means it sent it to him, not to all of us. So that's anyway. Okay.
Okay, so the question, I believe, if I understand it right, was really what's the difference between non-probing active adaptive management and what we're calling passive adaptive management. And the key here is whether, imagine you're the manager, do you take a decision today anticipating what you're going to learn in the future? And if you do take that into consideration, that belongs here in this box, this non-probing active adaptive management. If I, as a decision maker, maybe I know that information is going to arrive, and when it does, I will update my beliefs, but it's a complicated thing for me to anticipate all of that and fold it into my optimization problem. So I know I'm going to update in the future, but I'm going to ignore it right now when I'm choosing my optimal action. That's passive adaptive management. I will still update when that information comes, but I'm not folding that that information into my optimization problem. Okay, so happy to chat more about that in a follow-up, either a breakout room or a by email or later on if that's still confusing. Okay, so I want to just give an example of a Markov decision problem that I've worked on recently with, I think actually Lucas is out there somewhere. Hey, Lucas, he's Lucas is an economist working at USGS and I believe a participant in this workshop and was instrumental in formulating this problem. Essentially, what we were interested in is trying to figure out management to improve outcomes for humpback chub in the Grand Canyon that were being preyed upon, or still are being preyed upon, by non-native rainbow trout. And what was interesting about this project, it raised several modeling questions for us. One was if our objective here was the survivorship of this species to ensure that they stayed above a minimum viable population level. How do we maintain that over time? So we were dealing with thresholds. We were also dealing with joint chance constraints, which is a particularly thorny thing where we're not just interested in the survivorship of this species for 1 period or 2 periods or 3 periods, but really the survivorship over, say, the next 20 years or 50 years. So jointly across all of those periods, we're interested in the survivorship of this species. And that made it so we lost this Markov property, and I'll talk a little bit more about that later. We then had to use a penalty method to overcome that Markov property being lost, and so on. So this raised a lot of really interesting and thorny modeling issues for us. But I think it provides kind of a nice example to illustrate several pieces of this Markov decision process. Okay, so first of all, we've got this chub level here on the vertical axis, and actually the lower end of the chub is up here at the top. And this was really our minimum viable threshold here was 4,000. So we're interested in avoiding that level for the chub. They are preyed upon by these non-native trout, as I mentioned. So those are the 2 state variables that we were most concerned with. What's the level of the species, the good species that we want to maintain? And what's the level of the bad species that's preying upon the species that we're trying to protect? And then what's illustrated in this heat map here is the level of trout control. These are electrofishing trips. So we have no control here at 0 in this blue territory and very intensive control in the yellow area. Okay, so this is an example of that strategy, that optimal policy that we're seeking. That's what's being plotted here in this particular heat map. Not represented directly were the transition dynamics for these chub and how they depended not just on the current population levels of both species, but also the level of control that we chose. But what is pictured here, these white contour lines, that was given the optimal policy in this model, 10% of the time we expect the chub trout population to be here in this inner ring, 25% of the time within this next ring, and then 50% of the time under the optimal management policy, we expect the chub to be within this outer ring here. So it kind of gives you a sense of how those stochastic population dynamics for both of those species are moving around in this space. And overall, as our reward, which was not pictured necessarily here, we were interested in minimizing the total management cost of these trout control trips that were taken to control the trout. So minimizing that cost in order to achieve our particular viability objective for this species. All right, so that was a fairly complicated example, but I think a fairly interesting and fun one. Okay, so next I want to take us, give me just 1 second here. I'm gonna transition over to the whiteboard. So if you've received that, that link, if you found that link in the chat and you prefer to navigate over within the whiteboard itself, please do. Give me a second here to maximize the view.
Can someone put the link in again?
Link is at the top of the chat.
The top of the chat depends on when you came in.
Oh, excuse me. Okay, you're right. It's now at the bottom of the chat. Right. Right.
Okay, cool. So just to point out a couple of things that are possible here. If your view will be a little bit different. Over on the left-hand side, you should see this comment little symbol here. And if you click on that and then you go into the space here as I'm writing, you can drop a little comment if you're interested and ask me a question that sits out here in space. Oops. Go back into full view here. I got to figure out how to get rid of, okay, my comment's gone. So what I want to walk through here is an example of this, what I referred to earlier as a non-probing active adaptive management problem. This is going to be a 2-period problem that we'll work through, and it'll illustrate, hopefully for us, several important points, and give you a sense of a Markov decision problem that is interesting enough to include adaptive management, but simple enough for us to be able to solve it just on this whiteboard. Okay, so let me walk through what this problem entails. Okay, so to start off with, we have some sort of plot of land that's in a natural conserved state. And we've got to decide in the first period. So we've got some sort of action that we're interested in, and it's a very simple action set. We can either choose to stay conserved, so keep this keep this plot of land in a conserved status, or we can choose to develop it. Now, a key wrinkle here is that development is irreversible. So if we start off here as conserved, in the first period, we can either choose to develop or conserve. And if we choose to develop, well, in the second period, our only choice is to also stay developed. Conversely, if we maintain the plot in a conserved status, then in the second period, we can again revisit and choose between developed or conserved. So again, here, the second period, we're going to be indicating that with the plus sign, just as I had mentioned earlier, for indicating next period. Okay, let me clean up some of this notation here, some of these scribbles. Our reward is going to depend on whether we're developed or conserved. So of course, if you choose develop, you get the reward for developing. And conversely, if you choose to conserve, you get some payoff from this plot of land for it being in conserved status. The key here, though, is that the benefits or the rewards of conservation are uncertain. They might be either high or low, and we'll talk a little bit more about that in detail in just a second. In the final period, after you say either choose to develop or finally stay conserved, you get a final reward that is again determined by the reward, say RD, but it has an extra weight on it, W, and I'll talk a little bit more about that in a moment, make that a little bit more concrete, but I'm going to make that a weight that's bigger than 1, and this is just meant to stylistically capture the idea that the rewards that will follow are over a long run time frame. So maybe our initial reward here is over a short time frame. After we make our second period decision, we're going to get some further reward, but suppose that lasts over a long run time horizon. So one of the things that's happening here is we're taking a long run problem and really boiling it down into just a couple of periods. Okay, so I'm going to put some numbers to some of these elements in order for us to, let me just reorient our view here, in order for us to be able to solve the problem with pencil and paper. Okay, so suppose our benefits from development are equal to 10. That could be in millions or hundreds of thousands or whatever you like, but let's just keep it simple and call it 10. And we'll get a reward from conservation. And as I mentioned before, that's uncertain. So we might either have a low level of reward, let's say 6, or we might have a high level of reward equal to 12. Now, to keep things simple, the probability of both of those outcomes, let's say the probability of a low reward is equal to 1/2, and similarly, the probability of the true reward from conservation being high, let's suppose that's also half. Okay, so we've got 50% chance that this is a high value plot, or 50% chance that the value of conservation is actually low. Okay, so when we have uncertainty like that, it's going to be helpful to appeal to the concept of expectation. So what is our expected reward? To calculate that, we just take the probability of it being low times the payoff if it's low, plus the probability that it's high times the payoff under high. So the expected payoff from conservation is 9. 50% chance it's low at 6, 50% chance it's high at 12. In expectation, 9. Okay, so by design, I've chosen these numbers strategically, which might not be surprising. So just note that by design, the reward for conservation, if it's low, is less than the reward for development, which is known with certainty, but that's less than the reward for conservation if the conservation value is high. So this is what makes for an interesting decision problem. We've got a relatively certain value from reward from development, which is known with certainty, and the value for conservation might be either high or low. But our expected value from conservation is less than the reward from develop. So at least at the outset, in expectation, the conservation reward is going to be lower than the value to develop. But we'll see later on why conservation still might make sense. Okay. So next, we're in a 2-period problem here. So let's think about what the cumulative reward is across the 2 periods. So I'm going to abuse notation slightly here and have a function R that's a function of the actions in both periods. So we've got your reward from whatever action you take in the first period, and then the action you take in the second period. Is going to be given by this expression. So we've got your reward from the first period plus your reward for whatever you chose in the second period. And let's let W equal 20. So I'm putting a much greater emphasis on payoffs in the second period, since that's going to reflect payoffs that are really in the real world going to be over a much longer time horizon. Now that weight of 20, that's going to be, this is a technical aside, and if you're not interested in discounting, you can kind of ignore what I'm about to say, but that weight would be motivated by a discount rate of 5% and an infinite time horizon. So if we were to sum from time equals 1 through infinity of, now this is going to be my my discount factor here raised to the number of periods this is going into the future times the reward that I'm going to get. Suppose that reward is accrued over every period, often to a long run future. When R is equal to 5%, this whole thing is going to simplify to 20 times that reward, that constant reward that you might be getting over that infinite time horizon. So this is all just kind of a technical aside, but just note that this W equals 20, that weight for that long run payoff, that actually has some motivation behind it. Okay, so now we're in a position to tackle, scroll up here to the top, our first task of 2. Our first task is, let's solve for the optimal choice, assuming that no information is coming. So this is going to be a non-adaptive manager who completely ignores information or just chooses not to take it into consideration. All right, so let's think about what the payoffs are under the different decisions we could make. So suppose we chose to develop in the first period. That means we have to stay developed in the second period because that's irreversible. Then we would get that reward for develop in the first period, the extended reward for staying developed in the second period. And given the numbers that I specified below, that's 10 plus 20 times 10, or 210 to make it concrete. Okay, so let me pause there. If you've got a question about this expression, it would be a good time to ask it now. And Suzanne, let me know if you're getting any questions coming in the chat. But we're going to look at some more complicated cases. And so I just want to make sure that that notation and those numbers are okay with everybody before we dive into some more detail. So I'll zoom out for just a moment. So
I think all is good. All is good.
Okay, so we've got the reward in the first period here, which we had earlier specified RD, and then the reward for staying developed in the second period here, this WD, and we specified that that reward was 10, so we've got 10 plus 20 times 10. Okay, so hopefully that's relatively straightforward. All right, so going into some of the more complicated cases, let's consider the expected reward from choosing to stay conserved, but then giving up and going to developed in the second period. Well, then we're going to get the expected reward from staying conserved in that first period, plus the long run reward for being developed. And we worked out those terms before, 9 plus 20 times 10, so 209. And then finally, the last thing that we could choose to do would be to stay conserved in both periods, in which case we get the expected reward from staying conserved in the first period, plus the expected reward of staying conserved in the second period, which is equal to 189. Okay, so we've got the expected reward from staying conserved in the first period and the expected reward for staying conserved in the second period, totaling 189. So just looking across these options, if we were to make the rational choice, given the assumptions over these rewards, what's the optimal choice? What is A star in the first period plus an A star in the second period? Well, it's pretty obvious, right? Here's our develop choice. Develop in the first period and stay developed. Okay, so we have a fairly pessimistic initial approach that comes from ignoring the capacity to learn. All right, now let's pop down here to our second scenario. Let's consider what the solution looks like for the optimal choice here under this adaptive manager who takes into account the arrival of information. Okay, so just as before, if we decide to develop and stay developed, this is the same as above. If you choose develop in the first period, the arrival of information doesn't really do anything for you in the second period because you're already developed. That's an irreversible choice. So this option looks just like it did in the first non-learning scenario. Okay, now here's where things are going to get a bit more interesting. This is going to be the one complicated scenario to try to work our way through. Okay, so what is the expected reward if we stay conserved in the first period, but then we take the optimal choice in the second period, conditional on the information that arrives? So this manager is one who's going to conserve in the first period and then take advantage of the information that comes through and then choose optimally based on that information. Okay, so in the first period, it's easy. We still just get our expected value from conservation. But then what do we do next? Well, if we stayed conserved in that first period, there are two potential paths we might end up taking. We could, with probability equals 1/2, learn that from our information, the conservation value is low. Conversely, we could learn with probability 1/2 that the value of conservation is high. If that conservation value is low, if we develop, we get 200. If we conserve, we get a low value of 120. So in that scenario, if we learn that the value of information is low, then of course, the optimal action is to develop. Okay, so if we learn, we get the bad information, value of conservation is low, we're going to develop. Now suppose we get the opposite information. Our value for developing is no different, but now our value from conserving, when that value of conservation is high, is 240. So if we learn that the value of conservation is high, our optimal choice is to conserve. Okay, so now we're through the complicated part and we're very close to the final payoff here. So with 1/2 chance, we will follow this path, learn that the value of conservation is low, choose to develop, and get a payoff of 200. And with another 1/2 chance, we'll learn that the value of conservation is high, and we'll get the high payoff. So we get 9 plus 220, which is equal to 229. All right, so hopefully you've been able to bear with me through this point. And now we get the key payoff. So here, under a manager that learns, the optimal policy is to stay conserved in the first period, since this 229 is greater than this 210. And then in the second period, make the optimal choice relative to the information that comes through. So we don't necessarily know whether we're going to stay conserved or choose to develop. That's going to depend on the information that arrives. That's the way in which we're being adaptive. And so here's a key note. Accounting for information So accounting for that information arrival causes the optimal policy to shift. From develop to conserve in that first period. Okay, so we can dive into a couple of other more interesting pieces of analysis with this, but I think in the interest of time, I'm going to pause there and just mention a couple of things. Let me zoom back out here to see our whole problem. Okay, so notice that when we conserved before and then did develop, we got this payoff of 209. But then when we paid attention to the value of information, we had a larger expected payoff. So this in some sense gives us an idea of the value that's ignored when a decision maker chooses not to pay attention to information, is in some sense the difference between those two options. So that's a key detail or key idea of sort of this in this context. It turns out to be this quasi option value, which is a technical term that's not critical to stick to or to really take in, but in this particular branch of analysis, that's some jargon pointing to that type of value. Another interesting comparison of value is to think about what the expected value of information is, and that is what would we do, or what payoff we get information? Well, that's 210. But then under information, we get an expected payoff of 229. So in this case, the expected value of information is 19. That gives us a sense of how valuable that signal is to us. How much better do we do under an approach where we take into consideration the learning? Okay, so I'm going to leave it there. If there are comments that people have, if you want, or questions that you have of elements of this that you'd like some more feedback on, or questions or clarification on, you can use that comment button and drop them in here. And this will be a live link, so I'll come back to this and see, even if it's beyond the time frame that we have today, I'll come back. And so if you've got a question, leave it there and I'll make sure and address it. Okay, so popping back over to our PowerPoint slides, let me proceed past that example we just walked through. And from here, I want to spend some time thinking about unpacking the elements of a Markov decision problem. So going into a bit more detail on these elements that we introduced earlier on. So first of all, I would argue that one of the keys to creative Markov decision process modeling, including adaptive management, which is a creative application of Markov decision process modeling, is thinking beyond physical states. So of course, it's very easy to think about the stock of fish or a stock of water or a stock of pollution as a state variable. And those are of course important, but really anything that changes over time and influences the dynamics or rewards should be thought of as a potential state variable. So that includes these physical states that are easy for us to think of, but also some other elements which might be a little less obvious. So in a fisheries-oriented paper recently, we treated the price and cost terms. So that was the price that the resource fetched when it was harvested and the cost of harvesting as state variables themselves, because those were evolving over time and entered into the reward function. It could be that some parameters of the dynamics are uncertain. So over here is a logistic growth model where we have an uncertain growth rate and also an uncertain and evolving carrying capacity. And those were evolving over time. And so those became state variables unto themselves. In another paper where we were interested in diversity as given by a particular genetic trait in salmon, this was their out-migration timing from a freshwater system to the ocean. We wanted to capture their genetic diversity, so we had as state variables the mean and the variance of that genetic trait. And then, of course, for adaptive management, our beliefs about anything salient, whether that's the physical state or something about the rewards or the dynamics or parameter, any of that is fair game in terms of modeling for our beliefs. And those belief parameters themselves will become state variables that we track over time. This guy down here, I heard Dave mention the murder hornet earlier on. This is just a visual representation of a paper, oops, not that one, that I worked on earlier, where we modeled incoming imports as imports that were transmitting or transporting non-native species from one country to another as a multi-armed bandit problem. That is, if you were inspecting these incoming shipments of trade, you had to choose between different sources of trade to inspect, and that's like pulling a given lever, where you don't necessarily know what the payoff is or the risk is from a given source, and so you're sort of learning about what the risk or the payoff is from a given source when you pull that lever and doing that inspection. Okay, so Dave talked in depth about some examples of different kinds of controls, so I don't think we need to worry about going into those into too much depth. So let me skip here to just sort of some general thoughts on thinking about the state space and thinking about the action space. This is, sort of taking a complicated real world and trying to boil it down into what does that state variable look like? What does that action variable look like? And we face often a task between trying to capture reality in the model, but also keep it simple and tractable. So when I face that problem, I like to come back to this question of what are we trying to achieve? If we're trying to achieve, if we're trying to illustrate, for example, some idea in the simplest possible way, like we did in this whiteboard example a little bit earlier, a few minutes ago, we can get away with just a 2-period problem, right? That's the simplest kind of dynamic problem we can have, is just 2 periods. Now, of course, there was some complexity to it still with the uncertainty and 2 different decision options, but still that was, in terms of dynamics, fairly simple, just 2 periods. We weren't trying to generate policy for the real world, just to generate and show some insights. In contrast to that, if we're trying to generate direct public policy advice that has substantial consequences, then we got to be probably a lot more careful and probably a lot more capture a richer representation of reality. So what's pictured here is a set of results from an analysis that I've worked on recently, where, as I mentioned in the introduction to the workshop earlier this evening, I guess depending on what continent you are, in North America earlier this evening, we're facing this question, presumably sometime in January, maybe February, of having a limited stock of COVID-19 vaccines to allocate in a particular country, for example, in the US. So suppose we can vaccinate 10% of our population in each month. So here's month 1, 2, 3, 4, all the way through month 6. And in each of those months, we need to decide what share of those vaccines, as given by the vertical axis, is going to go to a particular demographic group. So for example, here in pink, this essential workers aged 40 to 59. Now, this problem is fairly high stakes. We're talking about direct impacts on human mortality, where, for example, our objective might be to minimize deaths. So this is really high stakes. So we really tried to be as rich as we possibly could about allowing for the share of vaccines that go to a particular group. That's a continuous variable here. And then underlying this model is a rich set of states where individuals are either susceptible, exposed, infected, recovered, or deceased. So we have multiple different potential states that people could be in, and the share of the population that's in each of these is allowed to vary continuously. So that's an example of a much richer state and action space, but motivated by the fact that we're dealing with, that we're trying to generate public policy ready advice that has really high stakes. So we could think, sort of just laying out a continuum here from the simplest possible representation of a state or an action. In a degenerate case, if your action or state just takes a single value, then we would just treat that as a parameter and it really wouldn't be part of the state or action space. And then the next most complicated thing we could do is to have a binary action or state that's either 0, 1 or low, high, so on. Next most complicated would be a set of n elements, 0, 1, 2, 3, so on, or maybe low, intermediate values up through medium and then up through high. And then the richest representation of either a state or action space is typically, not always, but typically something that would be continuous. So taking an example, I'm going to start to introduce an example here from Paul's MDP Solve toolbox. So over in MDP Solve, he's got this example problem, simplepests.m. And so in that problem, your task is to think about treating a site to deal with a hemlock woolly adelgid problem, and you can either leave it alone or treat it, right? So that's a very simple action space. And then the state space, the pest level could either be low, medium, or high. So if you have downloaded his MDP Solve toolbox and you run simplepests.m, or you open up that M file, that MATLAB file, you'll be able to see that particular problem. Okay. One of the more complicated elements of the Markov decision problem is dealing with the dynamics. This process of transitioning from any given current state to a future state, in particular when we have uncertainty. So apologies there, I updated that notation. So it's a lowercase n is going to represent the number of different state variable levels we could take. And we're going to let little I and little j index a state level. So if the state level is little I equals 2, that just means the second to lowest state level. So suppose that we have some current state level little j, whatever that might be. We could think about, if we enter with that state into a decision period, what is the probability of transitioning to any other given state, anywhere from the lowest state up through the highest state, as we exit into the state that's in the next period. So this vector of probabilities just gives us a sense of what is the likelihood of heading to any one of these future states that we might end up in, conditional on where we're entering. Now, of course, if we were to add up all of these probabilities, they need to sum up to 1. That is, we need to conserve the mass. This needs to be a proper distribution. We need to end up somewhere. So the probabilities of any of these given states, that all needs to sum to 1. So to take a particularly simple example, if we had a 20% chance of ending up in state 1, 30% chance of ending up in state 2, 50% chance of ending up in state 3, this is what that transition vector might look like. Now, heading into the full problem, the Markov transition matrix is the name of this object, where we think about not just being able to enter in one particular state, like on the previous slide, where our state is little j, but we might have a starting state that's either the lowest state, the next lowest state, any given generic state, or the highest state. And given that, what is our probability of ending up in, say, any given exit state? So again, the sum of those probabilities for any given column is going to be equal to 1. So here's an example over here, again, pulled from Simple Pests. And note that our transition probabilities, those are going to depend on the action that we take. So in this Simple Pest example, you can either not treat or you can choose to treat. And the transition probabilities that we have will be conditional on that. So if we treat, and suppose we enter the problem in this middle state, we have these probabilities of exiting in any given state. So if we enter in the middle state, our probability of exiting in the middle state is 40%. So we'll get more experience and more practice with those in Paul's session tomorrow. Just as a quick note, if you don't deal with Markov transition matrices much, you might ignore this, but just note that sometimes people will specify this matrix in its transpose. So substituting rows for columns. So you can specify it either way. You just need to make sure it's defined and specified, whether the rows for a given column sum to 1 or whether the columns for a given row sum to 1. Okay, and we're about out of time, so I'm just going to make a couple of quick notes. This model for transitioning is for discrete states. Note that we had a description of those discrete states, that set of possible discrete states here, and we have a set of nodes in this, or a set of discrete elements in this Markov transition matrix. If we've got a continuous state instead, likely we're dealing with a function that's going to allow us to deal with those continuous states. That's going to map your current state into some future state depending on some random noise that might influence it. So just some simple examples here. Our future state might be given by our current state minus some, say, harvest, plus some shock. And of course, there's various ways that could be specified. We've got our reward function here. That's fairly straightforward. Some examples of that, our reward could be focused on some net profit, or we might be interested in simply just the costs of control, or we might be interested in minimizing the combination of damages and control costs together. So just to finish up here with a simple example from Simple Pests. Suppose we have damage costs for 3 different states. So this is the damage you experience if the pest is low, damage you experience if the pest is high or medium, and then damage if the pest is high at 20. And then here are our treatment costs. Putting those together, we can get to our final reward function that combines both the damage and control costs. So it's an example of that final one. So I think in the interest of time, we should probably end there. There is some complication. There's some additional detail with respect to the discount factor, but Dave's already talked about that to some degree. And then a final detail, which maybe we can pick this up at the beginning of tomorrow, is a key idea of the Markov property of a stochastic process. But that'll take a bit more time to unpack, so maybe we should save that for tomorrow.